Welcome everyone. So it's my great pleasure to welcome our today's speaker, Sida Peng from Microsoft Research. Yeah. And Sida got his PhD from Cornell in 2017, and he worked on a lot of cool problems like in econometrics and industrial organizations. And he's currently a senior research economist in the Office of Chief Economist at Microsoft Research. And today he's going to talk about a very exciting topic on estimating the effect of a new technology using a durational model for staggered adoptions. And let's welcome Sida. And by the way, just a heads up, if you have questions, you have three ways you can ask questions. The first one to type your question in the chat box, or you can just put it in on the Q&A, or you can just use the raise your hand function, and then we'll allow you to talk to ask questions. Okay, so Sida.
Great. Yeah, thank you, Vincent, for the intro, and thanks everyone for joining the talk today. I'm super excited about this project, and this is actually the first time I present this paper. So we don't have a draft posted yet, but we're going to have one very soon. So any kind of comments, any suggestions is hugely welcome at the time. And so there are still kind of plenty of things we want to do. We want to try on this. So yeah, please reach out, kind of just interrupt me in the meetings, or like reach out afterwards if you have any thoughts or want to discuss this further. Yeah. So this is kind of a joint project with Aureo Paula from UCL, and so what we are studying is basically estimating the effect of the kind of new technology. So using a staggered model for this, using a duration model for this staggered adoption process. Yeah. So so what motivates this? Of course, I'm kind of I'm from Microsoft, so like what we are kind of we oftentimes kind of have different type of questions coming from the product group, ask us like how to measure this, how to measure that, and so this actually kind of is motivated by one of those consulting projects we take. So one of the things we kind of interested is basically how we should measure productivities for the knowledge worker. Right? So the kind of evolvement of technology has been kind of wrapped up, it is kind of a rapid evolvement in the technology in the past 30 years, right? So this is basically like all the word logos. I don't know if like many of you still kind of remember those, but I remember when I saw those word labels, that when I was still in the high school. Right? So, but now it's more the new word label looks like this. So yeah, so there has been like many generations of the different words, and many new features have been added. But but when we think about like adoption of this technology, it's kind of a different world than say like 20 or 30 years ago, right? So people no longer like pick up a manual and then read all the instructions over there and try to learn something. And when they kind of learn about new technology, they're going to kind of use them immediately. That's no longer the word. Like nobody's going to kind of spend time like reading about even like the post about all the updates, details about like what's happening, like what's new in the Word, Excel, PowerPoint world, and then also like any training programs. I think like hosted by the Microsoft, there's a very kind of low attendance. So people kind of the active learning time of the kind of learning new technology has already passed. So people more or less pick up on those through the interactions with their peers during the workplace. Right? I saw my colleague using a new technology. I find it very productive and interesting. So I go ahead and kind of chat with them to say, hey, how do you find out this and how to use it? Right? So that's how you learn about new things. And it's kind of being replaced by this kind of peer learning and knowledge diffusion. Right? So and usually this actually takes quite a long time. So like what we observed in the data is for a new feature to roll out to majority of the employees within a company, it usually took 1 or 2 years. For kind of a typical S&P 500 company. Yeah. So one of the questions kind of that's kind of one of the problems kind of arise from this kind of slow adoption and this kind of passive kind of learning is that how do we actually measure the impact of the technology? Right? So if you think about the technology being adopted at one time, it's very easy. You could think about like even doing a random experiment. Like have the feature available to some other group, not available to the other group, and then compare whether there's any change in their productivity. Right? But because of this slow adoption and because this kind of self-selection into adoption, this question becomes more difficult. But it's still a very important question because like from the Microsoft side, we want to understand basically how effective our technology is. Right? This is going to be kind of becomes forming to form like the 4 key KPIs. We can measure the kind of the productive how the engineering works on the key features, or how the local sales representatives are actually promoting the product. And also we want to, from the customer side, they're also interested in learning about this to see if they are spending their money kind of getting something really worth it or not. So the things we are going to kind of talk about today is a new Microsoft technology called SharePoint. This kind of might be a little bit not familiar to the academia side, but kind of mostly used by the industry world. I think like from your side, you could just kind of picture this as a picture SharePoint as a combination of Dropbox plus Google Docs. Right? So what it does is basically it's a kind of cloud document platform where once you save your documents, say Word, Excel, PowerPoint documents in the online drive, and then the online drive of Microsoft is called OneDrive. And then in that case, at the time that you're sending these documents, either kind of as attachment or as a link to your collaborators, and then when they open it on their desktop, when they change anything on the document on their desktop, the same changes will be synchronized to your documents. Right? So in that case, what it prevents is basically like what it provides is basically the version control, and then kind of aim to kind of bring this kind of seamless kind of collaboration experience to our users. Right? So this has been kind of up for the past 5 years. And then in this, you can see it's actually being rolled out to a large amount of our tenants, of our customers. So 350K organizations have already adopted it, and then that's like 85% of the Fortune 500 companies also adopted. And so what the user experience looks like. So although like it sounds kind of very complicated, it's kind of a platform, but from the user side, you can just think about this as a kind of a substitution for your classic email attachment. Right? So that's maybe like the most advantage of this technology. That once you make any change to your Word document, to Excel document, you no longer need to kind of send that again and again as attachment to your collaborators. Like all you need to do is basically send it once. So on this, when you kind of try to write an email, and then when you now can try to attach click here and try to attach a document, you can choose whether to attach it as a share link, or you share it as a copy. So as a copy here is as the old kind of classical kind of attachment copy. A share link, this basically enables it to be a SharePoint document. So you are adopting this technology, and then all of the changes, of your changes, of your collaborators' changes will be synchronized on this document. So you only need to we truly believe that this technology is useful, there should be can you guys still hear me? Hello?
Yes, now we can hear you.
Yeah, we can hear you.
Okay. I just saw some internet unstable signal. Okay, yeah. So as this technology ramps up in a given company, what we can say is basically the reduction. What we should expect is basically a reduction in the number of attachments. Right? So here I'm taking one example of an SP 500 company. So from January 2018, we saw around on the left-hand side, this axis means, and the blue line represents a cumulative number of adopters. So adopters here are defined as you use the SharePoint, you sending the SharePoint link at least once. Right? So you will be counted as an adopter. And this is a cumulative number of SharePoint adopters from January 2018 to October 2019. Right? So this is kind of an increasing curve by definition. And then also on the right-hand side here, on the right-hand side of the axis, this is measuring the number of email attachments. This is being measured by this solid red line here. So we have some data breach in the middle of the area. So from October, I think November 2018 to the May 2019 period. So we don't, due to data breach, we do not observe what's happening in the period. But after the data has been restored, so you can see here, basically, there seems to be a kind of a decreasing trend in the number of email attachments. And also, I'm plotting here the dashed red line here as the number of emails divided by 6. Right? So 6 is just kind of a normalizer. So as you can see here, before this was almost kind of, if you think about like a kind of like if people, there's really no changes to their behaviors, and we should expect kind of a constant rate of email attachment with respect to the email sent. But here you can see the gap gradually becomes bigger and bigger. Right? So yeah, from this graph, all I'm basically showing are correlations of this. So the question we are kind of asking is that, is there kind of a more scientific way or kind of a more causal way that we can actually quantify the reduction of email attachment due to the SharePoint? So the ideal work, or the ideal scenario is that we want to, if you think about like how we want to do kind of an experiment, so we want to kind of basically compare a person who kind of adopted SharePoint versus another person who haven't adopted SharePoint, and then over time we want to see whether there's any difference in their email attachment. Right? But of course, like we're not have the luck to do the experiments in this scenario. So what we are using here is kind of a classical kind of identification strategy, like often used in economics and also in social science, called difference in differences. So what it does is basically we want to compare customers, so employees within this customer who adopt and their patterns of sending attachments before and after they adopt the SharePoint, and then in the meanwhile also control for the time trend, and then see if there's kind of any reductions. So yeah, so this might be a point we can kind of review a little bit about the literature here. So this is still under construction. So this is definitely not a kind of extensive list of what's happening in the world. Yeah. So but so basically like what we're combining here is first like the difference in difference estimates. So like in economics, this was kind of first being used to evaluate a different type of social benefits program, like unemployment insurance or disabled insurance. So this is Card and Kruger papers, where they just try to compare people's income before and after they took, say, the unemployment insurance, and then and use that to evaluate the benefit of this program. And not until like 2000 with the ACN Invents and also Abadi 2009 paper that actually quantify those framework in a theoretical way, and then overlay the kind of the identification assumptions that needed, or the so-called kind of parallel trend assumptions that's needed to identify those effects. Yeah. So the standard Dift-in-Diff estimates that only compares the kind of just think about just compares like two periods. So it's either before you adopt the technology or after you adopt the technology. Right? So there's also a kind of a rise of a new trend of literature here that's consider multiple periods. That if we observe, if people are adopting the technology in multiple periods, and then over time, how do we actually kind of use a different framework? That's in this estimation. The setting is very similar to what we are going to discuss in this paper. So this is kind of followed up by this line of reason paper. And what we are doing different than this staggered difference design is that we incorporate the duration model into the structure, basically using the duration model to account for how people are actually making the adoption in this process. And more specifically, we're looking for those unobserved heterogeneities that could be provided, that could be derived from those duration models. And this follows this. This is a kind of a very incomplete list of the papers. I know this has been kind of a field being extensively studied in the statistical world. So yeah, please let me know if I missed anything in this one. But what we're looking for is basically from the Albert Ryder and also Hans Hausmann, where they study the unobserved individual heterogeneities in the standard cost model, and then Sarah Kuya 2006, where she kind of looking for the network effects. This is also something we're going to incorporate in this model due to the kind of the peer learning nature of all the technology diffusion. Also, Frank Hansen, Ono, and Hu talks more intensively about the kind of the censoring issues in those type of models with observed heterogeneities. Yeah. And I think also this literature also relates kind of remotely related to a kind of I think a rising literature kind of on the multiple cause causal inference. So where when in this literature where people kind of consider there's multiple types of treatment and then kind of trying to control for unobserved confounders. segment. So here you could think about the multiple calls as the kind of the treatment at different periods. And then we are also kind of in a similar way try to identify the unobservables and then try to adjust for them in this instance. But we are deriving our results under the different framework. Okay, and a quick view of our approach. So I think I already talked a little bit about this, but so what we are proposing is a different estimates that accounts for the selection in the adoption. Right? So here, when I'm saying selection in the adoption, so you could just picture this as the kind of we are trying to if there's a kind of a latent effect. Let's say in people's adoption, there may be kind of homomorphies on the network, where homomorphy is just like different individual heterogeneities across different groups of individuals on the network. And say like you are from you may be kind of joining from you may belong to a product group which we do not observe. And then in this case, when your product group is kind of engaged in a big project, this is the time where you are more likely to learn about a kind of a SharePoint technology, because you need to work extensively with your colleague at the time of a project. But in the meanwhile, because of the project, you also may be sending more of email attachments. Right? So this will be kind of a latent confounder here. And then we are trying to kind of identify this confounder through modeling the adoption process and using this to back out the confounder and then adjust it in the identification of the treatment effect. So, and here within the different framework, what we are talking about is the specifically violation of one of the fundamental assumptions in the different framework called parallel trend assumption. I'll be more precise about that just in the next section. But when this is actually like this is a kind of a key assumption for identification of the different diff effect, but it's often observed to be violated in the real world application. Like even in for the previous paper I was mentioning, like there's a famous paper kind of defining this as so-called action filter diff, where they observe when people right before people taking up the unemployment insurance program, there is going to be a dip in their income beforehand, compared to the people who never adopt the unemployment insurance. Right? So this is exactly the violation that we are talking about. So we are trying to adjust, trying to account for those selections. Yeah. So okay. So yeah. So here is a kind of a outline of the roadmap of how I want to proceed. So first, I will discuss about the kind of the standard Dift-in-Diff estimates, and then talk about our kind of adjusted Dift-in-Diff estimator from a couple of stages about modeling the diffusion, also our identification assumption, and then estimation, and finally show some empirical results and simulations. So let me know if you have any questions at any time. Yeah. Okay. Yeah. Questions? Oh.
I think so far so good. I haven't seen any questions, so yeah, I think you can go ahead.
Great. Yeah. Thanks. Okay, so here let me revisit the standard Dift-in-Diff estimates idea. So let's consider kind of only individuals adopting at or after time t. Right? So just think about this as 2 time periods. So I use YT1 and YT0 as the kind of the potential outcome for individual I at time t. And then let me define this TI as the first time individual I adopted technology, and XI0 are kind of pre-treatment covariates. Right. So what we are trying to identify here is the so-called average treatment effect on the treated. So it's the potential outcome of individual I adopt at time t, kind of minus if it's not adopting at time t, and then condition on individual I is actually adopting at time t. Right. So this will be identified under the famous parallel trend assumption. So what this means here, so I'm using a graph to illustrate this, is basically if you think about like 2 individuals, I and J, okay? So I is adopting at time Ti and J is adopting at time Tj. And let's just think about like 2 time periods, time Ti minus 1 and time Ti. And then in this case, because J hasn't been adopted, so let's say the Yj minus 1 is kind of not adopted at this point. And then if we're moving in this trend until the time Ti, right? But on the other hand, Ti adopted at time Ti. So what we will observe is this solid line here on its trend. But here, notice that because Ti is already adopted at time Ti, so what we will observe here is Yiti for the potential outcome to be evaluated on. Right? So what parallel trend assumption is saying is basically if Ti is not adopting at time Ti, then if we're moving in the similar trend as Yj, and then in that case, this will be drawn by the dash line. So the difference here will be accounted as the ATT we're interested. Okay. So the question is like when will this parallel trend assumption fail? Right? So here I'm taking kind of alternative specification for the outcome. So let's say if we can write the outcome as say alpha I plus tau t, and then plus let's say first is Kasi IT tilde here, right? So this is kind of more like a kind of a nova decomposition. No assumption is being made on the alpha I tau t and this Kasi IT. And also we are kind of writing down this this DIT here, which represents adoption status of I at time t, and also multiplied by this omega IT. I should also mention that this DIT here defined, so we only allow the treatment to happen once, and then after the treatment happens, all the following up period you are being treated. So it's not the case that you can be treated in this period and treated in the following up period. It's once you've been treated, once you adopt the technology, you always adopt it. Yeah, there's no reverse back. Okay. Yeah. So if we take this specification and then we kind of take the difference and write it in the potential outcome, and then kind of take the difference of the untreated potential outcome, then the difference of this will just be tau t minus 1 plus delta the delta tilde Kasi IT. Right? So delta tilde Kasi IT is just Kasi IT minus Kasi IT tilde minus Kasi IT tilde minus 1. Right? So then the parallel trend assumption is nothing but an independence assumption, which is basically stating that for people adopted time Ti, and then its delta Kasi IT tilde will be same as people who adopted after time T. Okay, so like one of the ways that this parallel trend assumption can be violated, so one can easily construct to say this delta tilde Kasi IT can be written as kind of a composition of Vi delta eta t, and which is kind of, you can think about this as one of the factor case representation here, and then plus another thing, right? So if this Vi here, which represents kind of in our case is going to be the individual heterogeneity or homomorphism on the network, is correlated with your adoption status. Let's say if Vi took two different values, and then one of the group tends to kind of adopt earlier than the other group, right? So that's what causes correlation between the delta Kasi tilde IT with the treatment status. So then in this case, the parallel trend assumption is violated. So this idea is actually closely related to the kind of the ways that people often use to test the parallel trend. So what the way to test the parallel trend is that if in the case that we observe kind of in a previous period, so this is the plot we just saw on the standard Dift-in-Diff estimates. If we observe a previous period where I and J both haven't been adopted, say time t0, right? So in this case, if we would expect that they also move in a way that the parallel trend assumption should hold, in a sense that if we kind of compare the growth of these two trends, then the difference of this should almost equal to 0. Okay, so any questions so far? Okay, good. So now let me talk about our adjusted Diff-in-Diff estimates and how we are actually dealing with the presence of those the heterogeneity data. Okay, so what we do is we start by first modeling the diffusion process. Right? So to account for this kind of peer learning, so this is basically I'm plotting the kind of the email communication network for this S&P 500 company. Right? So this is kind of just a plot here. The different color just means different clusters. So we're not actually using the information of the clusters. All we are using is basically the email communication networks about the employees for this tenant. And so what we are doing here is we incorporate this network structure into the modeling of this header model. So let's say we define this lambda I tau here as the kind of the header of learning about the new technology. So here then we kind of modeling this as kind of in a Cox header model kind of setting, where this lambda 0 here is the natural rate of learning, and then this lambda here represents the kind of the bonus to the header due to the network effects. Right? So this Ni here is the set of neighbors of individual I defined by the email communication network, And then this DJ tau here is your neighbor's adoption status at time tau. And then multiply by the constant part here. But also we have the individual heterogeneity, observed individual heterogeneity ZIs being incorporated here. Right? And then here, because we're adding the ZI here, we need to do some normalization. Otherwise, lambda 0 and ZI are not jointly identified. So we normalize lambda 0 to be 1 in this case. And so here also we define this quantity script GI as the kind of the neighbor's adoption status until the time Ti. So with this notation and also with an additional assumption on the ZI, so we assume that ZI is independent of the XI0 and GI, and then in this case we can estimate the distribution of the joint distribution of Ti and also ZI. And that will actually allow us to actually back up the distribution of the unobservable ZI from this Bayesian equation. Okay, yeah. So now let me talk about how this this observed heterogeneity will impact the outcome equation. Yeah. So our identification. So here is the kind of outcome equation we just laid down, kind of inherited the same kind of notation from our previous kind of notation in the Dift-in-Diff estimates. Right? So except here we already can decompose the KCIT tilde with this VI eta t component. Right? So our identification strategy here is very simple. All we want is basically to restore the parallel trend assumption. So now let's assume if we kind of observe two different types of individuals, three different types of individuals. So similar as in the Dift-in-Diff setting, we have Ti who adopt at time Ti. We have individual I who adopt at Ti, but we also observe individual J and K who will adopt in a time that's greater than Ti. So they haven't adopted at time Ti. Right? So if we observe there is a different trend in the growth of the K of individual J and individual K, then this difference must be due to this additional component in the spectrum set. Right. So it turns out with some algebra, you can see that if we move this using a parallel trend, if you're using this parallelly to the individual K, the difference here will be accounted as Vk minus Vg multiplied by delta eta t, and also plus some air term. So let's maybe ignore the air term for now, and then just focus on the factor part. And then this actually allows us a way to actually estimate the delta eta t. So in a way that if we assume that Vk will be observed in this setting, and then we can just use the outcome of individual K and J at this time Ti, between the time Ti minus 1 and Ti to estimate delta eta t. And once we have delta eta t, we could use this to adjust the outcome for individual I. Right? So this additional component will be the impact on these factors on individual I. And then after we adjust for this, the parallel trend assumption could be restored, and then this the left component would just be the ATT we interested. Okay, yeah. So to formalize this, of course, like there's going to be a kind of a set of assumption we need. So this is basically our most important assumption here. Try to restore the parallel trend assumption. So one should read this assumption as kind of two components. So first, let's let delta t equal to 0. Right? So this is basically saying that without the factor components, right? So the parallel trend assumption will be held for because delta t equal to 0. So this would just be Ti equal to T, and this is Ti bigger than T. Right? So that's just equivalent to the parallel trend assumption we saw before without this component. Right? So the other component here is that when delta t is bigger than 0. Right? So this is basically saying for all the people who adopt in the cohort afterwards, and they would also follow parallel trend assumption at this time t. Right? So this additional assumption here would allow us to identify the delta eta t from like using the people who haven't adopted. Yeah. So then on the assumption 2, so we can see that this parallel trend assumption, which is this component, the component here, will be restored after one adjusting for this impact from the VI. So this we kind of, with the expectation, we integrate out the error term. So that's and because this two terms here will be identified from the adoption stage, And then in this case, it will allow us to first estimate delta eta t and then use this delta eta t to construct counterfactuals for the adoption for the counterfactuals at time t. Okay. So let me now kind of formalize the estimation procedure I just talked about, and also highlight some of the challenges we made. And yeah, so this is basically the first step is that we estimate this duration model. So one of the first challenges we met here is basically the data is less censored. So the data starts in January 2018, but at the time there's already 120K users who have already adopted. Right? So if you think about kind of trying to write down a likelihood function to integrate all of this this adoption, the issue is that we do not know the order of how this 120K users before the time January 2018. So this is going to be a very large integration and very difficult to write down the likelihood directly. So what we are taking here is kind of a different strategy, which we discretize the entire process and then try to simulate this and then use the simulated method of moments to do the estimation. So we're able to do this because we know when it's the first time the technology is available to the company. So this we can check with the finance to learn about when the first time they purchase. It's just from the time they purchase to the time of January 2018, we don't have a data pipeline built there to monitor their usage yet. So we do not have this data. And then starting from the time the technology is first available to them, we approximate the kind of the baseline hardware rate with this kind of discrete quantity here. And then we use this discrete quantity, we use this kind of approximate hazard to simulate the entire diffusion process until the time we observe. And then we construct the moments to match on the number of adoptions, and then estimate the parameters of lambda beta in the hazard process. And also talking about the estimation of ZI, so we want to estimate ZI kind of non-parametrically on the kind of a discrete support. So, but this is actually like a very computationally heavy procedure, given that we are actually also simulating the entire adoption process. So here we only use kind of 10 grid for the support of ZI. And then even this kind of we have to kind of using some of the most advanced computing. So we are using the kind of the GPU compute here to compute the entire simulation procedure and estimation procedure. Yeah. Okay. Yeah. So next, after we estimate the adoption process, then what we do is to estimate this delta eta t. Right? So here I'm defining this quantity, this width here, phi I GG here as the kind of the two components. So if Ti equal to G, it's going to be kind of a 1 over the probability of you adopting at time G. And then if Ti is bigger than, sorry, this should be bigger than G. Sorry, yeah, so this is a typo. If Ti is bigger than G, then this is minus 1 over the probability of your adoption after time G. So this is nothing more than the kind of the IPW, the inverse propensity score, kind of in the standard IPW estimate. But we are kind of writing this kind of in the staggered staggered outcome adoption framework. And then with this weighting, and then also under the parallel channel assumption, and also the kind of the independence assumption for the duration model. So now we will be able to show that the expected value of this quantity here. So here the YT and YT minus 1 are all observables. And then having this adjusting for this expectation here would be would have expected the value of equal to 0. Right? So in our estimation, this part will be plugged in with the first stage estimate, and by using a kind of least square estimate, we will be able to estimate the delta eta t. Yeah. So after having the delta eta t here, so now we are using it to construct our ACT estimates. It's going to be the same as the previous procedure, except that here now we are computing at the time exactly when the Ti equal to T, and then this will be kind of a similar weight here. So also a similar type of least square estimate, except that we will now have the delta eta t here being plugged in from the stage 2. And then here this function xi0gi kappa t here. So this kappa t here is just a parameterization of this function here. So if you think about this as just a constant or a kind of a fixed parameter of kappa t here, this was just nothing but giving you the ATT estimate. But here you could also estimate some heterogeneous effects if you have some kind of pretreatment covariance. A question so far?
I think so far it's so good. So far, so
okay.
good. No
Great. Thanks. Okay. Yeah. So let me also talk about another quantity kind of we are interested in to measure in this case. So which actually kind of leads to a stronger assumption that could be imposed. Yeah. So this is what we call it the effect of exposure. So previously, like when we compute this ATT here, it's only going to be the effect right after adoption, right? So this is only going to be for individual I adopted at time t. What's the effect of this adoption from time t to time t minus 1? And but oftentimes what we're interested is basically after 1 month of adoption, after 2 months of adoption, and how large will be the impact of this technology, and so on. So what we define here is basically the effect of exposure. So this has been defined as the difference on the potential outcome for at time t, if you are given for your adopted versus you haven't been adopted, given that you are adopted at a time which is t minus e. So and then we're taking integration of the distribution of the t. So here we also need a kind of a stronger assumption here for in order to compute this. It's basically to say that the parallel trend assumption still need to be held even after you adopt. Right? So this is even after you adopt. If you were not treated in many times of the previous period, you would just be grow similarly as people who never adopted. And then under this assumption, so we could just compute this time to exposure as a kind of a summation of the previous estimates that we generated from the three-step estimate. Okay, yeah. So with this estimate, so now let me talk about some simulation results and also our empirical applications. So first, what we do is that we give an estimation. We first kind of perform a simulation to kind of to show that this estimate could give a reasonable result. So this simulation is kind of generated based on some estimates from the real data. And this is first kind of we generate the diffusion process with kind of this is the neighbor's hazard rate due to a neighbor. So and also this is the beta here is set as this. So we use the covariance of your average number of emails sent and average number of time you read emails as our covariance. And then we simulate this diffusion process for 24 period with the first 3 periods being censored. And then the underlying network is exogenous given from the real data. And also this network this data set contains around 10,000 employees. And for the individual unobservables, we take the AI as a kind of Bernoulli distribution, taking value 1 and 2 with probably 0.5, almost around 0.5. And then all of the kind of outcome functions is being generated with all those alpha I, tau t, KCIT being generated from a standard normal distribution. And then when we choose the eta t here, the factor loading, and we choose it to be minus 2t plus epsilon t. Right? So in this case, the delta eta t will just be minus 2 plus the difference of epsilon t and epsilon t minus 1. And then the treatment effect here, where with omega it is minus 2 multiplied by the time of your exposure. Yeah. So with this, so here what we plot on the left is basically the we so-called like pre-trend estimates. So what we do is that we apply the different diff estimates right before your adoption. So in that case, this is going to be kind of a direct estimate as the kind of the placebo test I was talking about earlier, and because you haven't been if the parallel trend assumption holds, and because you haven't adopted at the time, So we should basically expect a 0 estimate. Right. But here, as you can see, that without the kind of with the standard Diff-in-Diff estimate, what is plotted by the blue line here, we clearly see a kind of a rising trend here, and basically showing that the parallel trend assumption is being violated. Yeah. And on the other hand, if we kind of plot this estimate using the adjusted Diff-in-Diff estimate, and then you can see this is almost centered around 0, which means the parallel trend assumption has been resolved. Yeah. So here, this line here is being reversed. Basically, this is so 0 months till your adoption. This is 1 month till your adoption. This is 2 months before your adoption, 3 months, and so on. Yeah. And on the right hand side here, so this is the kind of the effect of exposure. And one should read this graph as this is the effect of exposure of 1 month after you adopt, 2 months after you adopt, and 3 months and 4 months after you adopt. And since this is cumulative, so the magnitude is different than the one on the left. And as you can see, for the standard Diff-in-Diff estimates, you can see here this is it's above the kind of the true effect, which is the kind of a slope of -2, which is highlighted by the black line here, and this is almost going to coincide with our adjusted Diff-in-Diff estimate. And I should also mention that the dashed line here is the kind of is not a confidence interval in this case. This is just 200 simulation with the 95 quantile. So yeah. So now come to our empirical application. So in this SPF SP500 company, so we observe 244K employees, and with an average of 55 email attachments sent per month. So the email network has 879K connections, and with the average degree of centrality is 3.6, and average closeness centrality is huge. So this is a network where like in the middle, like people connected very central, but there's also kind of different leaves that's going to be extended quite largely to the edge of the graph. So first we show that the parallel trend assumption will be rejected. I will show the results in the next slide. And what we find is basically there's going to be a cost adoption. The first month after you adopt the technology, there's actually an average increase of 1 attachment after you adopt, and then we saw a kind of a decreasing on your number of attachments. And after 10 months, on average, you're going to reduce your email attachment by 25 pieces. So then this is highlighted in the plot over here. So here, this plot is similar as the kind of the simulation setting, where the only difference here is the dashed line here is not simulation. So here is the 95% confidence interval. So I should also mention the way we build confidence intervals is through parametric bootstrap. So because given the kind of simulated method at the moment, there's really no way for us to do the kind of any non-parametric bootstrap in this case. Yeah, so what we can see here is basically for standard Diff-in-Diff estimates. So this is before you adopt the technology. This is the month before you adopt the technology. You can see here there's a rising trend here. So basically coincided with the intuition here that once before you learn about technology, it's more likely that maybe your group has a shocking productivity, so that you start to interact with your neighbors and that with your colleagues, and that increase the amount of work you need to do and the amount of email attachment you need to send. And on the other hand, if you kind of apply adjusted diff estimates, that's a parallel trend assumption will be restored. And on the right hand side, this is the kind of the overall effect we saw. So here is this kind of around in the first month of adoption, we saw around the kind of an increase of 1 email attachment. With the time kind of becomes larger, almost until 10 months, we saw kind of almost a decrease of 25 pieces of email attachment. But if you are using a standard Diff-in-Diff estimate, you are significantly underestimating the effect of reduction. Okay, yeah. So I think this is all the talk here. So as you can see, I don't really have a conclusion here because I think this is still ongoing work. I don't have, I think there's still much things we want to try, basically kind of try to improve the method of movement estimates that we talked about in the first stage estimates. So if you have any kind of thoughts on that, and either kind of on computationally or the method to estimate, we'll love to learn more about that. And also, like from any other aspect of the paper, please let me know if I have any thoughts or comments.
Okay, great. Thanks, Sida. Any question for Sida? Okay, I think I'll start with a few. Actually, it's a very great work and very smart idea about accounting for this like latent compounder. So if I understand it correctly, the ZI denotes the latent compounders, right? So it's not directly observed, but I think in your method, you need to estimate the expectation of ZI given a couple of things, right? So I'm just curious that in this context, how do you estimate that conditional expectations?
Yeah, so let me go back to that slide to see if this is your question.
Yes.
Okay, yeah, so this is basically like we write on the header of the kind of the cost model, and then what we are doing. So ideally, so let's forget about the kind of the centering problem. So one could just write down the likelihood of this, and then just directly estimate the coefficients inside the kind of lambda, beta 0, and also the kind of the distribution of ZI. Right? So once you have the distribution of ZI, you should, and also the kind of the joint distribution of TI and ZI, you will be able to back out the distribution of ZI given TI from this.
I see. Okay, yeah. Okay, great. I think I missed this part, so that's why I thought like, okay, that's unidentified, but great. I think that's great. And I have another actually questions about like I was wondering like because we know that adoption might have some uncertainty. First, it may have some uncertainty time, and I think another reason like even if I adopt say to the SharePoint, I may still sometimes I was just not fully really adapted to SharePoint, so I may still have like still use the attachment or something else. So I'm wondering like, is there any way to kind of account for the uncertainty or like kind of learning effect, right? Like it's adoption. Although I think ideally want to just use to like a binary to simplify the scenario, but there might actually be a more like saturated process on that. So I'm just curious. Yeah.
Sure. It's just to clarify on the question you're asking, like, are people kind of still using the email? Is this a question or?
Well, I'm still using email even if they adapt it.
So email attachment. Right? Oh, for sure. Like, I mean, this you can read that from the kind of the last result here, right? So what? So over here. So like on average, like people find 55 pieces of attachment, right? So like our results show that even after 10 months, you only reduce the email attachment by 25 pieces. Right? So that's basically saying like on average, people still even after you adopt. After you adopt 10 months, you're still like sending around 30 pieces of attachment. So I don't think the kind of SharePoint is kind of the way to completely replace email attachment, because I think like this technology will only be useful for people within the same organization. Right? So if you are trying to share with the people outside of your organization, depending on your security compliance settings, I don't think sometimes they will not allow you to do the direct share. So you still have to send out your results to classical email attachment. It's definitely not something directly kind of replaced. So what we are showing here, so we are not what we are not looking at is basically the increment of the links that's being sent. Right? So that would be like another thing that you want to look at. Basically, how much would one link worth of email attachment, right? So, but what we are looking here is a kind of indirect measurement on just how after you adopt. We don't care about your activities after your adoption. Maybe you are kind of just use it once and forget about it. But whether there's any changes in the email attachment, which should serve as a kind of should be substituted out at least kind of fractionally by the SharePoint.
I see. Yeah, that's a good point, because actually I was also about to ask the question like, because sometimes people actually might get used not because they don't do attachment, but they could just sending something in the hyperlink, like, and especially like like there are a lot of good big company like a Dropbox and like a Google Drive. So sometimes they may just send this instead of sending an attachment over they're going to use that instead. But yeah, so that's something I guess. But I don't know, in your data you might be able to get some hyperlink, like checking the number of at least to see whether the number of hyperlinks is actually increasing, I guess.
Sure. Yeah. So like I think like email attachment here is just one example, right? So I was talking kind of more generally about like measure productivity of knowledge worker. So you can imagine here like using the same kind of same methodology to measure like other outcome variables. For example, like the kind of the hours you work, right? So all the things like the time you spend on certain apps or the time you spend on kind of on kind of writing emails, or kind of collaborating with others, having meetings, and all of those could be kind of measured by this kind of when there's a new technology roll out to impact the a certain metrics. Yeah, so this is kind of just an example, but what we are interested here is to kind of provide this framework to the product for them to use. Yeah.
I see. Okay, great. Other questions for Sida? I think people are just, it's Friday afternoon here. So people are probably just, very exciting about having a weekend.
Sure, yeah, me too.
Okay, so if no other question for Sida, thanks Sida, and yes, thanks for giving a talk. It's very interesting work and very exciting, very smart idea. I like the idea that you can actually accounting for this latent variable fact. I think actually there's a growing interest. I think to how do we deal with this latent confounder problems?
Yeah, thank you so much, and thanks everyone for joining me today on sharing this. Yeah, please don't kind of hesitate to contact me if you have any thoughts afterwards. And yeah, thank you so much.
Okay, great. Thanks, Sida, and thanks everyone.
Thank you.
Thank you.